might as well get started. I'm still sick. My voice still sounds a little bit messed up. Still dealing with really runny nose, all the other stuff, all that other fun. So the good thing is we're pretty much ready to start PCB layout, but there's a couple little things I want to get done, cover first real quick before we do that. I am going to want to throw mounting holes onto this board. We'll throw 4 of them in, so we're going to create library entries for them. Again, the good thing is they don't need to be put in Odo. Right now, we shouldn't have to worry about Odo right now. I'll just create the library file. We'll just create the library files. I'll show you a couple little tricks we can do with that. And then download. So we'll do that. And then I want to real quick create a logo library. That way we can keep logo files. We're going to throw together. I threw together a real quick logo, but I want to run you through a few things that would be more specific towards the ECAD software. I know it's little things in like with Altium and Circuit Studio, even Eagle, they like a specific format, and we'll do that real quick. So in KiCad, what we're going to do is I'm going to do things a little bit differently. I'm going to create 2 new symbol libraries. File. New library. It's going to be a global library. Okay, so create a new library. Let's see, KiCad library. And we're going to call this one mounting. Let's call it hardware. We're going to call it hardware. A new symbol library. And before we get too far ahead of ourselves, let's go over here, create a matching footprint library. It's a global, and we're going to call it, well, after we get into where it belongs, we're going to call it hardware. Okay. So what we're going to do is in this, let's do the footprint first. Okay, so we're going to need a few bits of information. So I'm going to go ahead and we're going to use M3 for the mounting holes. I like it. It's a good size, relatively low cost. We're going to assume that it's going to be like a pan head Phillips screw. Real idealistically, you could use anything you want. We're also going to assume a washer. So a few things we got to do. We want to make sure that we size the hole and everything appropriately. So what we're going to use is we're going to use a pad. We're going to use a through hole pad. Let's see here. Place. Let's you. Oh, I've got to create a new footprint. Okay. So a lot of times, MH, they'll use MH for mounting holes. Let's get these guys out of the way. Okay. So we're going to go and just save this real quick as M3. M3 mounting hole under hardware. Okay, now we're going to be able to throw in a pad. We're going to throw in a pad. Okay. Now we get in the property, so it's not going to be a SMD, it's going to be a through hole. Okay. We're going to want it round, circular. Now we're going to need to know through hole, diameter. Okay, hole shape. Okay. Now we're going to need to know our overall diameter. So since we're going to be planning to have a washer sitting on this, we pull up what the ISO standard sizes for washers are. So if we're using an M3, we'll use this chart the standard diameter for an M3 washer to ISO standard is 7 millimeter. So what we're going to do is we're going to make the overall pad 8 millimeter. Okay. Okay. So 8 millimeter. Okay, so I made the pad 8 millimeter. Then let's go back to another reference that references the standard ISO clearance sizes for holes themselves. So for a 3 millimeter, you have a coarse measurement, a medium measurement, and a fine measurement. You typically want to be in the medium size, which in this case would be 3.4 millimeter, to account for any variances and tolerance stack-ups in any hardware you buy. This will give you a pretty good wiggle room. So if it's just if the hardware is bigger than the ISO standard size, this will just give you that wiggle room just in case. So we're going to go with a 3 millimeter hole, but the standard is, the actual diameter is 3.4 millimeter. So we're going to go back to here and give it 3.4. All right. So we have that. You'll have the exposed copper there. All right, let's see here. Anything here that we need to be worried about? Okay, connections, clearances, that's fine. Don't need to worry about any of that. There's no solder paste. It's a through-hole pad, and it's not checked here. So we're going to hit OK on that. So now that's kind of cool and all, but what would be nice to have is a 3D representation of a washer and a screw to throw on here. So what we're going to do is we're going to go to McMaster-Carr. And I've already kind of selected a washer. It doesn't matter. We're not buying these washers. We're just a great source for the 3D CAD file. So what we can do is we can actually download the step file. And okay, so we've got the step file for the washer. And I just chose a panhead Phillips screw. And McMaster-Carr is a great source for hardware for long-term reliability. And there's a few other reasons for that, other than being a large, reputable company that has, I've never really had any problems with them. So as cool as we can have it with threads or without threads, we're just going to go in and accept the threads. So we have now the 3D step files. All right, so we have those guys. But one of the things I want to show you, one of the reasons I like McMaster-Carr for ordering hardware, let's just go back to here real quick. Not only do they have a very large selection, I mean, we got thumb screws, round heads, pan head screws, hex screws. We pretty much got the full gambit. Great source to go to. But one of the things is this guy right here, the material certificate. And this is the certificate of conformance, basically. So when you order any product out of here, you'll automatically get a certificate of conformity. Basically, it's traceable. So if, especially if you have a process that demands it, that all your products be shipped with certificate of conformance for material standards, or if you have a customer that requires it for their own processes or their own end customers, that's another reason I like McMaster-Carr is automatically right here. Sometimes you can request materials, the CFC for other products, for some of their other products, but sometimes it just takes a little bit more time. This just speeds that up. Yeah, pricing, they're a little bit higher than you expect, than you would find for something on Amazon. But I do want to address that elephant in the room about, if you're planning to build a long-term business, Amazon's great for prototyping, short-term stop gaps when there's a material shortage. But because it's difficult to get certificates of conformity from any of their vendors, most of them are unknowns. They're their names just pulled out, out of a hat and just thrown together just to make sales. Unfortunately, they're just rife with companies that come and go. There's no long term. You can't really plan a 5-year shelf life, a 10-year shelf life with a product, using products that you can't guarantee their availability for the next 5-10 years. At least with a company such as McMaster Carr or Mauser, DigiKey, Newark, the large players in the space for hardware components, you can generate 10-year shelf life plans. You can generate, manufacturing plans. There are some customers that demand that you do a part analysis and make sure you can supply the parts and materials for 10 years, because that's what they want to do. They want you to be able to manufacture and ship them finished product for the next 10 years. And unfortunately, I'm not bashing against Amazon. They're a great service, a great company, but when you're trying to create a reliable business, you don't want unreliable vendors, because Amazon they're not the only ones that sell the products on there. Anybody can technically register a business account and sell products. And therein lies the problem. So this is just one of those things I want to cover. You just want to make sure you can plan forward. So we've downloaded those 3D step files. We're going to go into KiCad back here. All right, so we got here. We're going to go and save that, and we're going to go into properties. All right, 3D models. If this works like any of the other software, I can actually put in multiple 3D models. So we're going to start with the washer. We're going to see how that sits. Oh my goodness, that's so beautiful. So notice there's a little bit extra, and that's to account for the wiggle room on washer sizes on variations. All right. So then we're going to, we can. All right, let's throw the screw on top. Okay. Now we're going to, no, I don't want to scale it. Offset, my bad. Point 2 1. And not to be perfect again. So what's nice about this, I chose I think it was a 6mm screw. That's another great thing about companies like McMaster Carr and all them, is the availability of 3D stuff, of their 3D files for engineering purposes. What's great about like Fusion is you can download straight from McMaster Carr for your designs. You can actually go pull up the catalog in Fusion, if I remember, I haven't done it in a while, and actually download the step files for their products. So when you're actually doing enclosure design, you can have everything from their site. So one of the reasons I like doing this is if you ever need to export this board as a step file, yeah, it can be annoying, but the right software package can actually go in and extract and get rid of these screw holes, like SolidWorks. I think you can even do it in Fusion and separate it. And so this step file you can actually get rid of in Fusion, so you don't have to look at it or deal with it. But this makes it great, so you have a real quick representation of what your board with the mounting hardware is going to look like in an enclosure. So I like doing this. We're going to save that. So we have the M3 mounting hole. You could take the time and develop a whole library of mounting holes, like for common hardware that you want to use, like M3, like panhead, by M3 panhead, by 8mm, and actually have the screw representation and all that. You can actually take the time. I'm just looking for real quick process to kind of show you one of the things we can do. So we're going to create a new symbol. We're going to call it M3 mounting mounting hole. And I can drive it. MH as a default designator. Blah, blah, blah. We don't really need to show that. Don't really need to show the pin names or numbers or anything. Actually, you know what? We might. We'll fix that. Now, so one of the things I wanted to make sure I didn't do is, so I've seen mounting holes done in multiple different ways. I've seen where some engineers ring vias all the way around the mounting hole to ensure it gets a good ground plane. But with electronics design, we'll cover that in a minute because I don't want to deviate too far. Let's get the mounting hole done. It will have a pin, so maybe I'll fix that, but I'm not worried about it right now. So we're going to basically just draw a circle. All right. We will throw a pin on it. 1 and 1. I will make it passive. All right. Okay. Oh, there we go. Hello. Now. Hello. I don't know why I like it over here better. So, now what we're going to do is we're going to save that. Now we're going to go into properties. We're just going to kind of, we don't really need to worry about all this. We need a value, but for the description, we're going to do standard hole for M3 sized fasteners. We can go here. ISO, I'm going to forget that, but we'll do my best here. Actually, we can do follows. ISO 273/1979. Can do that. We're going to hit OK. Actually, we're not because we got to give it the footprint. So now we're going to go to hardware and 3 mounting hole. Okay. Okay. Now we're going to save it. Now we're going to come into our schematic, and I think we have to symbol libraries because we have to make sure that let's get rid of that one. So we have now we have that. So now it can be part of the project. So now we should be able to add that to our schematic. And for reference, we're going to have we're going to have 4 mounting holes. Now, here's something I'm going to see if I can copy. Let's save some time here. Let's see, mounting holes. No, let's capitalize that. Let's just go mounting hardware. Let's be fancy about it here. Stop doing that to me. Yeah, all right, here we go. mounting hardware. Oh, you know what I'm going to do? Because what's going to happen is, all right. So here's where we're going to cover something too. All right. So I'm not going to connect these to anything right now. So I'm going to throw in the no connect directive, because there's something I want to clear up. So if you're new to electronic design, you're just a hobbyist starting out following this video series, or if you been doing general electronics for so long, you may have forgotten or may need a refresher. So there's actually, so ground in a circuit is kind of a misconception, misconstrued, misunderstood a lot of times, and a lot of us just fall into the bad habit of not understanding it. You technically have three types of ground in a design. You have what's called signal ground, and that's what we're gonna call this, signal ground. So let's just go here. Let's go to grounds here. Ground. So I'm gonna just put that eye there. I don't know why I did that. So you're a signal ground. Now that symbol, I really need to learn how to use KiCad better. Oh, wrong button. I want to use the power. And then let's find the other one. See if we can find the other symbol in here. All right. No, that one's kind of used differently. Okay, so I'm gonna put these in order. I typically see them and use them. So you typically have your signal ground. This is basically your local power supply, like your 5 volt, your 3 volt power supply, the 24 volt coming in from whatever power supply it's using. This is basically your electronic local power supply. Then you have one that's typically called chassis ground. So this would be in a metal enclosure. It's the actual metal enclosure that it's using. The metal box would be grounded. Typically the metal box is grounded to earth. So in a way, you could bypass the chassis ground and go straight to earth ground. But a lot of design software and I'm included, in this, I'll use this symbol for ground because we're so used to using it. But technically it's not right for general electronics. Generally you're talking a signal ground. Technically they're not the same. So if anybody who's watching remembers anything from general electronics, let's get rid of chassis ground, because basically what it is, that's the metal enclosure the device is sitting in. Well, we'll keep it for now. Because earth, a lot of times you'll use in actual power supply, like real power supply. Like if you're pulling in mains power, like from, your 110 outlet, because that is tied to earth ground. That ground is considered earth. That's where you would use this symbol. And then it's the DC output from it for like your design. Technically isn't supposed to be tied directly to earth ground. It becomes then a signal ground. And I'll just show you a couple of things. So earth ground is basically the earth itself. But so what you can have happen is a difference between earth and ground. More of the modern systems can take care of that differential. And it's usually not that bad, but there can be a power differential. There can be a voltage present on earth ground that's different than your localized ground, and there could be some interference. It's not typical as long as the rest of your system is properly grounded, as long as your main AC power is properly grounded, you're generally going to be okay. but it is possible for there to be a difference. Now, a lot of times you'll see, let me see if I can rename that. Yeah. Chassis. Okay. So here's a lot of times what you'll see. So a lot of times, let's copy this and paste this up here. So a lot of times you'll see, yes, a direct connection between chassis and earth ground. It's a thing called ground strapping. When you ensure that all the chassis components, like a door, access panel, anything that can be, broken away and, still hang on to the machine, you ensure that it has a good solid connection to the rest of the chassis and then to the earth ground itself. It's typical ground strapping. But, so you want to make sure, so if you have if you're following proper design protocols, you would have your chassis ground and your signal ground. So mounting hardware, as seen on the root, you would typically tie this to chassis ground. And then here what you would do is, I'm just throwing some stuff in because we're not going to tie them in. You would just kind of do some calculations. Here we go. We're just going to, you don't need high capacitance values. Basically, if you want to, you would honestly choose better capacitors than this, and you would use a lot more of them. It would take some time and research. I don't typically do this because a lot of my devices are automation, and maybe I should apply this principle to this design. I might down the road. I don't know, after some testing. I might not worry about it because there will be isolation because it doesn't connect directly to main. But a lot of times what you'll see, get this stuff out of here. Get out of the way. And I know SkyCat would probably be mad at me. A lot of times what you'll see in designs are something like this. This is called basically stitching capacitor array. Sometimes you'll find a bunch of these that will be tied around your ground plane, your actual internal signal ground plane, and the mounting hardware. So you'd see a bunch of stitching capacitors over here, tied to each one of these. And what that does is it gives the voltage differential a way to kind of jump across the capacitor. It's mainly a safety that will help jump any, rapid changes in voltage, mainly on this side, jump it to chassis ground. That's what the capacitor will do. That sudden change will automatically sync to the other side because it will technically be, for that moment, an AC voltage. So there'd be a bunch of math and investigation to do to figure out all the right values for your stitching capacitors, your capacitance values, and the voltage rating that they have. Mainly, that's what that is. You would be stitching. They're isolated, but yet they're stitched together in a way that the capacitors would allow that real fast voltage differential to jump over. I just want to clarify that sometimes you do not want to tie your mounting holes to your localized ground plane. Sometimes you do. It's really dependent on what you're designing, what standard you're trying to follow, and your ultimate goal. For this type of device, since technically the power supplies themselves isolate, we won't be, we're not designing the AC power supply into this. We're going to be using something like here, let's just go to here. So let's, I don't know if you can find it here. No, but Master Car, I think, would have one. There we go. Something like this. We're just, okay. All right, well, let's just assume one of these power supplies. Many of you may have seen these. They're using a lot of DIY open source 3D printers. different voltage, current values, and you get, you know, output voltage. So let's say 24 volt DC output current. We want this guy to put out like 6.4 amp. And yeah, we're not buying one of these. I'm just showing you. So basically, we would be using something like this. These power supply like this are built really well. They handle their own internal isolation from the mains to the DC. So we don't have to worry about the chassis grounds or anything. We shouldn't really have to worry about that with our design. This will handle pretty much all that for us. All we'd be concerned with the output would be the positive and negative. So for our design, these would just be non-connected. But again, I left them as pads, you know, that you could electrically connect them to chassis ground or physical earth, depending on your needs. So I just wanted to cover that before we got too far along, because it's way too easy to ignore things, and I don't want to ignore things because that could put you at risk. The next thing I want to do is just real quick, a logo library. We're going to add a new library. Global. All right, and we're going to call it logos. The reason I like creating all these different logos, these different logo libraries, or, you know, libraries for different, it just makes it easier to find what you're looking for, update the main library for specific purposes without having to root through 1,000,001 things. Yeah, you could break down the components into capacitors, resistors, but at the end of the day, they're just components, and that's why we have a part naming scheme to help with that. Because you're not always going to use, you know, mounting holes. You're not always going to use logos or whatever. It depends what you're doing. This is just my preference. You can do things the way you want them to do. So what I did is in GIMP. Now I don't know yet on KiCad. I haven't tried this yet, but I do know with Altium and Circuit Studio, they prefer a specific image format, basically 2-color. If I remember right, it's white, what you actually want to display on a black background. But they really enjoy, well, you could do like JPEGs, if I'm not mistaken, raw bitmaps. A lot of times you'll lose detail, or the system will get confused on what you actually are intending to do, and you'll end up with just a blank or just a solid white, because you're technically only working with either printing or no printing. So basically 2-color. Your solder mask color, and then your silkscreen color. So what we want to do is, I usually convert this to, I go to mode, indexed. So I've done this before for another project. So we're going to do a 1-bit palette, black and white. We're going to convert it over. I created this as a 10mm by, so it's 10 millimeters tall by 40 millimeters wide. Now we're going to file, we're going to save as. And I'm just going to throw in here. I'm just going to throw in the resources. I'll give you the GIMP file. I don't mind. Generic logo. 10 by 40 millimeter. Save. Now we're going to need to export this. Export as. We're going to do bitmap, BMP. All right. So what it should, oh, well, we can probably do it here. Sometimes you just, Windows bitmap image. That's fine. So we're going to keep the name. I think these are fine the way they are. So what we should be able to do, go into here, into logos. We're going to create a new footprint. We don't need the reference there. Don't need that junk. So we're on the top silk screen layer. I think what we do then is place. All right, I have to figure out how to Should have looked this up sooner. I blame myself. Import graphics. Okay. File. We're going to go to resources. Wait a minute, what? Wait a minute. What in the world? Hello? File. Okay, that's even crazier. I thought there would be a, tools? There should be like a, is there a tool at the main menu for, graphics editor? No, image converter. Okay. Oh, shoo. Okay, okay. That threw me for a loop. Okay. Generate logo here. Open. All right. That's fine. It's just the way. Okay. Okay. I don't know what that does. We're going to do the footprint. We're going to put on the silk screen. Oh, okay. Oh, all right. Let's see what this does. Huh. CAD library. Logos. We're going to go to logo 10 by 40 mm. Save that. All right. Save. It must have. All right. Honestly, this is new to me. Okay. Let's delete that. All right. And I think what we do. Oh, there we go. Okay. Huh. So I think we need to invert that. All right. So let's go back to here to the image converter. Let's source image. Go here, and I think we negative then. All right, let's see what that does. Logo. Let's see what that does. Yes, let's replace it. Go back over to here. Aha, there we go. All right, now let's get rid of that. Perfect. So now we have a logo as a footprint. Well, as a footprint. So let's go ahead and create a symbol library. It just makes life easier. Logos. And then what we're going to do is we're going to throw a new symbol. Or you can call it logo. It don't matter. Oh, no. No, logo. Logo 10 by 40 millimeter. Default designator. LGO. We need this as one of any pins. Okay. Now, what I'm going to do, we're going to just draw a little rectangle. We're going to do the logo 10 millimeter by 40 millimeter. Bam. Hooray. All right. Not like any of this matters, but that's okay. We're going to save it. We're going to go to symbol properties. We're going to get our footprint. logos. All right. All right. Save that again. Close this. Don't need that. Go here. I'm going to pull it in here. Oh, that's right. We got to fix the symbol libraries. Look at it. All right, logos. Oh, wait, does that. Okay, save. Now we should be able to add it. Now, let's throw that in there. What's great about this, now you have a defined universal size logo, and you can create all the ones you want for different sizes. So typically, companies will use you'll use like an SVG file, scalable vector graphics for like your company logo. That way, it can be thrown on your website. You can throw it into business cards, any documentation, and rescaled, and it'll just scale up and down infinitely because it's vector format. And then you could do some fancy tools, maybe use GIMP or another tool like it, and export it and resize it to specific sizes. So your logos, you can create a universal brand, like a universal setting. So now we'll have this 10 by 40 millimeter logo that we can just pop into a design at any time, and it should transfer over to the board. Okay, so now that that's done, we've got mounting hardware thrown in here. We've got a logo mounted thrown on here into our cover sheet. Fiducials, we got all that. Real quick sanity check. Okay, bum. We got our inputs. We got our voltage rails tied in there. 5 volt, 3.3 volts. That's the 03 version. That's the 05 version. We got LEDs, test points. ESP32. Let's go ahead and throw in these not connected directives for now. Again, this is the first spin. We should be fine. 3v3, 3v3, 3v3. That's the enable. Just a real quick overview, just a real quick sanity check to kind of make sure things are here. Now, I don't know. We're going to test something here because I know a lot of the annotation got kind of messed up. The components got weird names, weird part numbers. I mean, annotation based off of like how we're moving things around. Okay, so everything looks fine here. Your 3v3 coming off. All right, so I wonder. Okay, I wonder if we can. Okay, we're going to reset existing annotations. We're going to do that. Okay. Oh, okay, sort symbols by either X position or Y position. It doesn't really matter. Okay, bum. Okay. See. Close. All right. All right, so that should have relabeled all these parts. If you're going to do things like that, you're better off doing it now before you translate it to a PCB. There's a lot. I know with the other software packages, the net becomes named. I don't know what the priority is, but the nets will share names like the 24 volt plus 24 volt, R2, R1. They'll be part of the net names, D2 and their connection points. So one thing I also want to mention, one of the other reasons I really like doing sheets for specific functions like this is it's easier to have them grouped like this when you and kind of limit instead of try to cram as much as you can in one schematic sheet. Because when you transfer it over to the PCB, it's going to be much easier to group all the parts together. So here we go. This file. So everything's saved. All right. Switch to PCB editor. All right. Just not. Okay, cover sheet. So it wants to be named after that. So, I almost don't care what it's named. Okay, cool. It has this stuff in here. Okay. Now, a lot of times it would be here, and I think there would be like an electrical rule check. Electrical rules checker. Let's see if it flags anything. Yeah. So this is typical a lot of times. Input pin power not driven by any output power pins. Now it's complaining about this guy. Oh. Are they not tied? Wait a minute. Maybe they didn't get tied together? Huh. Let's make sure it's not complaining here, because maybe we overlooked something. Which is kind of weird if that did happen. So let's do this. Because if these are flagged as issues, we want to make sure they're fixed. Markers. Let's run ERC. Okay. What in the world is this thing doing? Markers. Run this. Okay, why is it finding some? And some of them I just fixed. I don't care about these input power not driven. Those aren't a problem. Yeah, I don't really care about that error. CN1. Unspecified passive or connect. Okay, so it's making some unconnected wire and. Okay, it shouldn't matter. I mean, so we do that. Oh, let's see why, but you know. Wow, okay. This is annoying. A pin. Oh my god, okay. Wow. You know what? That's okay. Let's just tie you to that guy. I don't want to run all day running through this. Unspecified power input connect. I don't really care about that. Local globals have the same name. There should be an option. Typically, there'll be a project option. Let's just see if there's project options where your globals, like your ports, will rename your locals. So let's get rid of those errors and close. Preferences. Let's see if we have anything here. Getter, field names. It should be like project profit preferences. We'll worry about that stuff in a bit. I mean, yeah. Not really seeing it. Is it under preferences? Am I missing it? None of that. Printer, we're not doing that. Usually there'll be options. So no, they're like project options to where we can I'm not gonna worry about it. I'm gonna see what it does. I'm gonna see what leaving things alone do over here. Because having net names, your local versus your global name the same, again, technically, you could actually have it so a global, sets the local. So they share the same name. And that's typically what I would do. So we've got this. Let's see here. What are we doing here? Board setup. All right, board setup. All right. So what are we doing here? Board physical stack up. So we're going to, because of the number of signals, we want to do a minimum of 4-layer board. But because of the signals, and we might be able to, want to try to condense the size down, we're going to go to actually a 6-layer. We're not going to worry about any impedance control. We're just going to use theirs because we're not going to export this. We'll define a lot of this when we come back, or when we actually order, because we want like a board thickness of 1.6 millimeters. We're going to have your outer copper layer set at 2 ounce. We'll get into all that. So our main concern is the physical stack up. Design rules. Okay. Constraints. All right. So project is missing a read only. Project is missing. So, oh, probably because we haven't saved it yet. Save. Okay, here we go. Now, a couple things we're going to want to do is we're going to kind of predefine some of our standards, our information. So let me see if I can find some notes here. All right, because if I can refer to existing notes without having to dig up other stuff or make stuff up out of my head, because you kind of want to standardize for things like vias, trace width, pardon me, I should have been more ready. Because we want to kind of have a via size for a signal via, and then so those are, okay, those are constraints. So those are the constraints we want to try to follow by. All right. I apparently don't know what I'm doing. I wasn't properly prepared because I was kind of expecting to not meet this point so soon. Covered a lot of the things faster than I wanted to. So let me see here. Let me pull that off and just ignore my goofiness here, because I didn't mean to not be as prepared as I should have. Because one of the things I have, all right. All right. Okay. All right. Just ignoring that. So I have a, to open it. I open a separate code. Series resources. So where are we at here? I was supposed to open it. Where did you open it? All right. Where did you open? design standard. Okay, so just kind of opening here. All right. My bad. So we're going to actually, so we're going to go and throw this. We're just going to kind of copy this. We're going to come down here. We're going to just kind of, this will be a work instruction in the long run. File, we're just going to call it, we'll give it official names and stuff when we're done. Paste all that in. Close that because we don't need it. All right. So we're just kind of clean all that up. We're just getting rid of all that. All right. We'll keep kind of this because again, we're still going to follow ISO. We're still going to have everything here, but so we want standards set for like signal vias, power vias, your trace width, your trace spacing. 1 ounce copper, 2 ounce copper is pretty close. Via to pad clearance. This is all your clearances. So these are standards you want to try to follow. Mounting hole diameter, 3.2 millimeter. These are just standards you want to kind of follow, like your board edge clearance. I'm just going to drag this out of the... Well, no, we'll leave it here. Let's go back to this guy. All right. So minimum clearance, that's copper to copper. Why did I do that? Because I'm goofy. All right, so basically that's your spacing, 0.203 millimeters. Minimum track width. That's as small as we're willing to go for our, there we go again, hitting the wrong thing. The minimum width we're doing. Okay, minimum track width, 0.127 millimeters. Minimum connection width. All right, annular. Okay, so that is, okay, so minimum via diameter. So let's see here, that is the overall diameter. All right, minimum 0.559. And then I think the minimum annular width, let's see here. Actually, do the math on this. It's basically your wall. So let's see here. Your diameter, your minimum signal diameter is 0.559. We're going to subtract the hole diameter, 254. 0.305 divided by 2, 0.1525. Okay, copper to hole clearance. Basically, it's your clearance. Basically, pad 0.15 millimeter. We'll leave 0.25. That should be fine. Copper to edge clearance is basically this, 0.5 millimeters. Minimum through hole. That's okay. Micro via silk screen. Minimum text height. Minimum text thickness. Okay. That's pretty cool. Let's see. 0.635. Okay, predefined sizes. All right. Tracks with vias. We're going to do so our basic signal via. We're gonna run more signal vias than we are power vias. So 0.559, 0.559. All right, and the hole diameter 0.254. Okay, so that'd be that. Track is minimum. The basic is going to be 0.127 millimeter, I think is what we defined. Yeah. All right, so we have that. Tracks, vias, differential. We're not going to worry about differential pairs. All right, teardrops. We're not worried about that. Okay. Although we'll probably add teardrops, but this should be fine. Net classes. Not going to worry about that. Custom rules. I don't know. Constraints. No, there's some constraints missing. Okay, thermal relief spoke count. 4. So one of the things I was kind of missing, hopefully we can do copper pores on here. I really do. So this should, yeah, teardrop, custom rules. I don't know how we can apply. Can we create a rule? Well, we'll have to figure that out. Okay. Go and save it. All right. So we kind of predefined some of our board parameters, our constraints. That way it'll just make it easier when we start running things. So, file, import. Now, how do we bring in the components? That is the big thing. Okay. Place footprints. Okay, there's this. That's not what we're looking for. I'm trying to figure out how we import. So save it. Okay, this is where I'm lost because there's usually a way to pull in maybe it's the autoplays. Tools. Clean. Place footprints. Place softboard footprints. That does not work properly. What the world? What am I doing wrong here? That doesn't work. Maybe I gotta bring in the net list. All right, load test net list. No, because we don't have a file. All right, how do I push from the schematic editor into the PCB layout? This is where I get a little frustrated here. All right. All right. Let me move this out of the way. That way it's easier for me to reference without switching back and forth, back and forth. Ooh. All right. How do you bring that in? Are you serious? Really? Oh my god. All right. So the people behind KiCad, if you check this out, check out other applications that can handle this automatically. Okay. So we have to create a netlist. Let's go to root. Oops. I don't really care about electrical rule check right now. Tools. Oh, wait a minute. Update PCB from schematic. Is there something here? Okay, that's what I'm looking for. Why aren't you working? KiCad. Schematic grayed out. All right. Tools. Okay, so it says in your schematic. Wait a minute. Do I have to go here? Tools. Oh. Hey, this is where I get frustrated. All right, that. Okay, that does not make any sense. Okay. All right. Okay, so apparently I did something wrong. Project. All right. Huh. What's that here? Are you telling me I have to fix all this? Are you kidding me? No, I don't want to create it. All right. So tools. Verify them. Click on schematic editor. Wait a minute. Verifying file. Okay. Okay. Right. File. Close project. Open project. Oh. All right. Yeah, that's what I did wrong. No, why would I? Okay, some of this is not making sense to me. Why in the world? So I have the PCB. Okay. Okay. Oh my god. All right. What in the world? So I have to figure out how to associate these schematics with this project. Okay. All right. What tools? File. Can I tell what project it belongs to? So I'm in that. Tools. Oh, file. All right. Browse project files. All the files are there. They're just not associated with that. New project. So I've got project. Got the project open. Okay, this is going to drive me to madness. So, archive, refresh. New project. I got the project. Oh. Separate ESP32, separate controller. It does not exist. What in the world kind of crack are you smoking? Hardware. Yeah, we're going to figure this. I'm going to have to figure out this mess. Figure out what in the world went wrong. Because the schematics are here, but somehow they're not associated. All right. Here's the schematic. All right. Hierarchy. No. Figure paths. Is that? No, I don't need that. Tools. Yeah. So I need to figure out how to edit. Wow. This is going to be a lot of fun. Schematic setup. All right. How in the world do I associate? Let's look at the PCBs there. Associated as the schematic. stepper controller. Oh. Yeah, okay. Hmm. E32 separate controller. Okay. Okay, I kind of like, okay. So that is the schematic. Page 1. Schematic hierarchy. File. All right. So let's try something before I flip my lid and flip my computer desk. Let's be adventurous here. All right. So basically, it wants this file. We're going to copy that. And then we're going to come here and rename that. Give that the name. All right, let's see how badly we break everything and how upset KiCad gets at us. Yay, you got to see my desktop. All right. All right, that fixed it. So now that's part of the plan. Yeah, I planned it. I planned that. Okay, let's see if this works. So it should bring up the same. Okay. Okay, the annoying way to do things. Tools. Update PCB from schematics. No footprint. What in the world is your problem? No footprint aside. FID. Close. Let's get in here and fix schematic editor. No, we don't need a schematic. My bad. We need the symbol editor. Components. File. Did I not? Yep. Footprint. Yep, that was my fault. Components. Okay, I probably forgot to save it. That was my fault. So now, oops. So we're going to go into the schematic file. Go here. We're going to, we should be able to update symbol. Update all symbols. Let's just do that. Not going to do that. We're going to do close. All right. Save that. So now we should be able to do that. Tools. Why is it giving me no footprint assigned? Let's take a look. Don't you dare be broken on me again. Components. File. Properties. Yeah, well, it's got that footprint. Maybe, is there a way to update? Okay, that's got that. So why didn't it update symbol? Okay, footprint. Let's reset that. Okay, let's update. Oh. Huh. There we go. Close. Okay. We're gonna save that. Boy, learning more and more. Okay. Boom. No errors, warnings. Okay. Update PCB. All right. Close. Oh wow. Okay. Oh, look at there. Our logo's there. Okay. All right. All right. All right. All right. So I like to usually just throw this stuff off to the side. All right. Cool. 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 That's interesting how it groups it all together like that. I will say it's kind of neat. But hey, we've begun the layout process. Had to work through some headaches, but you know, that's fine. That's fine. That's fine. That's fine. I have to figure out what those. I think the green are interconnects. What in the world are the? Oh, I see. That's just showing that that they're kind of far away from. Okay, that makes sense. That makes sense. Okay, that the designators kind of slapped around a little bit. Okay, now we should be able to. All right. Okay, that was a way to jump. Not routing yet. Now there should be a way to nope, we should be able to define the board shape. Draw rule areas. Yeah, I might have to Google some of this because there's usually a button to define the board, to edit the board shape. Properties. Zones. Let me Google it real quick because I want to just. I had define. How do you define the board shape? Well, it looks like we just draw it. That is going to be interesting. Board outline. Okay. Well, it looks like we actually have to draw it ourselves. Let's just assume that's what we have to do. Let's just throw. All right. What layer? Copper. So there should be a typically there's a board. Oh. Huh. Usually you would draw an outline. Let's see here. Usually be mechanical layers. Okay. Copper, adhesive, paste, silkscreen mask, user drawings, comments, margin, board edge back, setback outline, user defined. What's it? Front, courtyard, margin, board edge cuts. Oh, the perimeter. Okay. Yeah. All right. So what we're going to do, we're just going to kind of suss out. Just suss out something. Hi. All right. So we will end this here. There's a lot to really get going. Just kind of suss this out. We'll fix this in the next video, the next stream. Just I might have to look a little bit more into KiCad. Again, I'm learning KiCad. I'm used to Eagle and Altium Designer and Circuit Studio, how they operate in their workflow. So learning this has been it's been a journey. We'll just say that it's been a journey. So we got the basic PCB started. We got our components slid over. We've got basics of a PCB outline. I'm gonna have to see about doing snapping and things like that, as it's a little bit easier. But I thank you for watching. I really appreciate it. If you like what you're seeing, definitely like and subscribe. And have a good evening. Catch you later, and until next time.